All right, so let's kind of begin to go through some stuff on that assignment. And I've already told this to my third block AP chemistry class. So once we start full time back on the 25th, okay, you all do realize, like this assignment is going to be due like before you all leave, okay? This isn't going to be like, oh, we'll hand it in like at 10 o'clock tonight on the CAM scanner app. Adeline?
Every single day since the beginning of the year?
Huh?
Nothing. Fine.
Yes.
I'll just change my ways.
I know. So I'm just telling you, if you want to begin to change that mindset, because once we go back, your physical paper goes in that physical tray at the end of the hour. Okay? So if you need some more time, maybe after school, that's fine. But I'm going to need it that day. Now, if every once in a while, Adeline Hill, you say, hey, I'm swamped, can I get it to you the next day? That's fine. But that's going to be rare, okay? So I'm just telling you, some mindsets might need to be tweaked a little bit. Okay, so let's talk about index of refraction. So, and light and how you perceive things. So, light is actually one of the coolest things in terms of how we are able to perceive the world around us. So if you look at the entire spectrum, from really, really, really long radio waves to extremely high energy like X-rays, okay? And in this whole gambit in between, there's a very, very narrow band of visible light that we can see. And that's okay. We don't want to see the entire spectrum, okay? I don't want to see microwaves. I don't want to see radio waves. Otherwise, you would just get so inundated with signals, it's like, oh my God, what do I process out? Okay? So it's okay that we just see a pretty narrow band of the electromagnetic spectrum. So you have two main equations. You have the speed of light equaling wavelength times frequency, okay? So as long as the speed of light is a constant, unless you're going through some other different type of medium, speed of light remains at a constant value. So that means there's an inverse relationship between wavelength and frequency, okay? So if you look at that spectrum, okay, and I'm guessing at some point you all might have been taught Roy G. Biv. Do they still teach you all that? Mm-hmm. Okay, Roy G. Biv. This is the colors. It's red, orange, yellow, okay, up through violet. So red is the longest wavelength. Violet has the shortest wavelength. So if you look at red light, that has a relatively long wavelength. Violet light has a relatively short wavelength. So here's the inverse relationship. So red light has a longer wavelength, okay? So with a bigger wavelength, it's going to have a lower frequency. Violet light has a higher frequency and a shorter wavelength, okay? So these two are inverses of each other. So what allows you to see colors, okay, is the idea that the energy is H times F. I learned it as H nu. So we'll do calculations with this later. This is what's known as Planck's constant. It's just a number. 6.26 times 10 to the negative 34 joule seconds. It's a very, 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 very small number, okay? But it's just a constant. So here's what you need to know for today, is that what determines the color that you see. So when I look at Josh's shirt, okay, and I see that montage of colors, okay, the greens, the reds, the whites, okay, what I see as colors is white light is being emitted, it's hitting his shirt, and what I see as green is the fact that it actually absorbs every color but green, and it reflects green off. It absorbs all the other colors, okay? If I see red light, it absorbs every color, but it reflects red, okay? So if you see black, okay? So if I look at Mr. Carter's letter jacket, right, that's mostly black. So that's absorbing most of the colors and reflecting a very small portion of it, okay? I look at the white on Ryan's sweatshirt, okay, that little bit of white there, that's actually reflecting the entire spectrum of colors. And it's not absorbing it. So this is why in the summertime you want to wear light colored clothes, because of the fact that it's reflecting that spectrum. If you wear a black shirt out on a hot summer day, if you like what Adeline has on, she would bake on a hot summer day, because that shirt is going to absorb that energy and not reflect it off. Okay? So if you get into so supposedly, they're calling for a pretty massive potential snowstorm to hit Sunday night, Monday, okay? You're gonna have this blanket of snow out there. So and if you ever go mountain climbing or around snow, it's very, 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 very bright when the sun does come out, because that white snow is reflecting all of that light. And so this is why if you're mountain climbing on the higher altitudes and around a bunch of snow, you get snow blindness because of the fact that it's reflecting all of that light. So here's what's important. What determines the color that you see is the energy of the photon, because that hits your rods and cones. So if I look at Josh through my glasses, okay? So if you look at what has to happen, light photons have to go strike his shirt, okay? So he's being bombarded with billions upon billions of photons right now. It isn't like he feels like, okay, turn off the light, I can't breathe, okay? Right? It would be really like, yeah, you turn on the light, okay. So, stop!
I'm just imagining that.
I know, it's just be awkward.
Like
Okay.
a cannonball hitting him when the
Yeah.
lights turned off. Sorry,
Yeah.
I'm done.
I know.
That's just funny.
Yeah, but if it was a white shirt, it would like bounce off.
Yeah.
You know.
Then everyone would go flying.
Oh, okay. Anyway, so the photons are being emitted, they're hitting the shirt, they're bouncing off of it, and my eyeball is picking it up, and I see green, white, red, the whole spectrum of the color, okay? With Joel, I see maroon, okay? So what I see is based upon a certain energy of those photons. Now, when I put on my glasses, now what's happening is that those same photons now have to travel through this lens. When they travel through that lens, okay, it's optically dense, and that light accelerates when it hits the glass, but that acceleration is making it slow down a little bit. But then it's going to speed back up, okay, once it gets out of there. Now that's the million-dollar question, is that, well, how does light speed up and slow down, okay? That has to do with electromagnetic radiation. We'll get into that later. But here's the point. Whether I have my glasses on or not, I still see the same colors. So what that means is that what's determining what you're going to see is determined by the frequency. The frequency stays the same. That's why I see the same color. The wavelength doesn't affect it. It's all about the frequency. So if you look at this equation, that C equals lambda times your frequency, okay? Now, as it travels through that light's going to slow down. So this is going to be a little bit less than 3 times 10 to the 8th meters per second. So the only way that can happen is if I maintain the same frequency, that means the wavelength is going to become a little bit shorter. Okay, so as you go through more optically dense materials, glass, water, okay, things like that, the only way that happens is if the frequency stays the same and you alter the wavelength. So your maximum wavelength is going to occur in a vacuum. The more optically dense it is, the more that wavelength shortens, but your frequency stays the same. That's why you see the same color. Okay? Everybody cool with that? So when you look at this question 17, so on that first question, you got frequency is light, is the frequency that's higher, lower, or the same after light enters a piece of glass. Okay? Don't make it difficult. it's going to be the same. That's why you see the same colors. Does the velocity change? Yes. Does the wavelength change? Yes. But the frequency stays the same. Okay? Now, so when you look at this index of refraction, okay? So your index of refraction, N, is the speed of light divided by whatever that new velocity is. So when you look at indexes of refraction, your maximum velocity for light is going to be in a vacuum, 3.00 times 10 to the 8th. So clearly, the smaller this number is, the bigger that value of N. Or some people like to think of it this way. They take N times that velocity to get the speed of light. So this also shows us inverse relationship, because these two numbers multiplied together always have to equal the speed of light. So as N becomes bigger, your velocity becomes smaller. Okay? And again, all you're doing is you're changing the wavelength, you're not changing the frequency. Everybody cool with that? Okay, so the bigger that index of refraction is, the more that's going to change. Okay. Now, the other big equation is this, what's going to happen on question number 4. If you look at what's going to happen on question number 4, you got a double slit experiment, the entire spectrum is immersed in water. Do the fringes on the spring get closer or further? Okay. So, on number 4, that's brought to you by this equation. Now, how are we going to do this? Stop that camera. We're going to move to the back of the room for just a second. That's what I'm going to do. So when I turn this on, I've got 2 speakers
Diego seasick.
that are producing this tone. Okay? So when you look at your variables, so this is like what I tried to show you yesterday. So this is the source of the sound. So the sound is coming out emanating like this, and this one has sound emanating like this as a wavefront. Okay? So this distance between these two is going to be d. Okay? That's the distance between whatever this is. So on the test tomorrow, you're all going to have a problem. It's going to be the very first test. It's going to be, excuse me, the very first problem. And instead of having speakers, I'm going to have 2 radio antennae that are emitting radio waves. Okay? And by the way, I'm going to tell you this right now. Even though it's a radio wave, it still travels at the speed of light because it's electromagnetic radiation. Tomorrow, when you have the test, don't sit there and go, oh, it's a radio wave, it travels at the speed of sound. No, it's electromagnetic radiation. It travels at the speed of light. Okay? Because I've had that happen. It's like the kids saw radio waves and thought, oh, I hear it on the radio. It must be traveling at the speed of sound.
That's definitely
I
how
mean, we'll probably do the same thing.
Okay? So that's why I'm just telling you. Tomorrow, when you get the boat and radio wave problem, they travel at the speed of sound. Or speed of light. Okay, so this distance here is going to be d. So then, what I'm going to have you do is I'm going to have you walk across like this, okay? And you want to turn this way so you can hear the sound. And some people can really hear it really, really well, and some people, they just can't. So if you have like a musical ear, okay, right, Josh?
I have hearing loss.
Alan?
No.
Okay. But here's what you should be able to hear, okay? Like when you're standing here, this should be like as loud as it's going to get. So this is what we call the central maximum, okay? So when you look at the equation like that delta y, what that delta y is representing is the distance between the central maximum and the next place where it gets loud, okay? And then the next place where it gets loud. So this is a double slit experiment. So there's 2 ways that you can do this. You can have like a light shining, and this is what I did yesterday with the laser. I had a light shining here, and then the light was coming out and emanating. That was like that double slit experiment that I showed you with Captain Quantum or whatever, okay? So that's an option, or you can just have 2 sources of this. So this distance here is d. Where you're going to be walking out here, this is L, okay? It's the distance where you're gonna hear. Your delta Y is going to be how far you have to move, and then you have the wavelength, okay? So that's gonna be your lambda. So what we're gonna do, and then I'm gonna turn this on, okay? And you can take Diego and
Diego,
see.
you wanna try?
We can try it, okay? But what you want to do is you're going to turn it like this, so you're kind of hearing one ear, and you should be able to hear like a central maximum here. Now, it won't go completely silent when you get here, okay, on a minimum, because you're still going to be hearing that other sound, but you should be able to hear it at a central maximum. Walk a little bit, you should hear it get weaker, because then you're having destructive interference, and then it should get louder again where you have constructive interference. Excuse me, constructive interference. Destructive interference, constructive, and it should get louder again. So I'm going to turn it on, so just take your time, walk across.
All right. Joel and I will take you. Diego. Joel, say hi. Wait, say hi. Say hi to Diego.
Tanya, stop this.
Wow. Funky rhymes. Sorry.
Okay, all right, so somebody try it.
Actually, I have hearing loss. I shouldn't go first.
Tanya, stop this.
Actually, take that, and I want you to walk with that camera too.
I have like severe.
We're going on a trip.
Okay, we'll just hope for the best.
So if you stop right in the middle, okay?
I thought we were just supposed to walk through. I was like, okay.
Okay, now start to walk, and you should hear a difference in the tone,
A little bit.
okay?
A girl with the hearing loss can hear it. Let's
Okay, Mr. Carter, try with the camera. Okay? You see it kind of get
You can kind
quiet
of.
and louder
Yeah.
again? Okay, all right, so now you can shut off that camera. What?
We're like barely halfway through the year, and you're just like, just turn it on.
We're more than halfway. Okay. All right.
You, Lauren. I owe you and Joelle a cookie. You do owe me a cookie. It better be a vegan one though. That was to Diego.
I'll take chocolate chip with pecans. Okay.
There you go, Diego. You know what to do.
All right. So if you look on question number 4, this is a situation where you have to kind of think through this a little bit. So number 4, you've got, there's the screen, right? And that's what I tried to show you yesterday with when I had like that laser shining and it showed that those fringes. And so you're going to do this in water. So imagine that here's the laser, and it's shining right on a screen, and then you've got this image back here, right? So we're going to put this whole thing in the water. So you put this thing in the water, what's going to happen to the speed of light in the water?
Decrease.
It's going to decrease. So what has to happen to the wavelength?
Decrease.
The wavelength has to become smaller. So we're not changing L because that's the length, like from the source to where you're hearing it, okay, or what you're seeing it. So L is a fixed value. We're not going to change D, right? Because that's either how far apart the slits are or how far apart the source of the energy is, okay? So we're not going to change L or D. So when it's going to be traveling slower, what's going to happen to that wavelength? It's going to become smaller, so therefore the delta Y is going to become smaller. So what you'll see is that those fringes are going to get closer together, okay? So with you guys, so if I could slow down sound, okay, so the frequency stayed the same. Well, what happened is that you would hear that central maximum, and then you would travel a shorter distance before you heard it again, okay? Or if it's light, it's going to be before you see that next central maximum. Yes?
Is that why sound sounds so weird underwater? Like as a swimmer, like it sounds so weird.
Well, number one, sound travels faster than underwater, and it was just like the opposite of light. Light slows down in water. Sound actually speeds up. And because of that, you don't lose that intensity of sound like you hear. And that's
Sounds
actually a
crisper.
concern. That you have all of these big cargo ships that are going back and forth across the ocean all the time, and they're afraid there's just like with the whales and dolphins, because they're so in tune to the acoustics of the ocean, and they evolved in pretty much a silent ocean. So that's a concern, is that you use echolocation or whatever, and the analogy is that you grew up in a fairly quiet house, okay, and that's what you're used to. Then all of a sudden, you have neighbors that move in that are continuously playing this horrible background noise, okay? Right, you're going to flip out, and they think that's what might be causing part of the problems with like whales that do like the mass beachings, is because of there's so much noise pollution in the oceans caused by all the cargo ships, and that sound travels so fast and doesn't lose that intensity that basically they're just always living in all this background noise. So that's actually one of the pushes, is to make ships quieter so that you don't have that continuous background noise for those animals that, because for millions of years, they didn't have to worry about that. And now all of a sudden, they do. So that's actually a concern.
Yeah.
Okay, so when you get on number 7, 7 is just a manifestation of this same equation, okay? Look at what's a factor, look at what's not a factor, okay? Now, when you get to number 3, problem number 3, you want to calculate the time it's going to take for to travel through this, okay? So here's the deal. Basically, you're going to, on number 3, you're going to look at the idea that you're going to take distance and divide it by velocity, and that's going to get you time. And so, and then you're going to add those values together. So on number 3, you're going to get in nanoseconds. Pay attention to the fact that they want this in nanoseconds. It's going to be it's going to be less than 1 nanosecond. Number 4, you want to calculate that speed of light.
Bless you.
Thank you. And then you should get something around 2 times 10 to the 8th meters per second for that one. Something around there. And anyway. And now let's talk about number 12, which has caused much pain and consternation to Adeline here. So when you look at number 12, so on number 12, you've got this 2 narrow slits this far apart, right? And so it's going to go through this one's going to go through like this. So the only way they can reinforce each other is if it's kind of like a resonant tube. They have to meet wavelength for wavelength, okay? So if you look at this conceptually, this one is going to travel a shorter distance than this one is, okay? Right? This one has like a longer hypotenuse. So the only way this can happen is if they reinforce each other, and the shortest possible thing that they can use to reinforce each other is 1 wavelength, okay? Because if they're off by a half a wavelength, they won't reinforce each other. So they're only going to reinforce each other when they're off by 1 wavelength. So on number 12, they give you a whole lot of information, right? And it says, how much farther did the light from the left travel than the one from the right?
550.
Yeah, it's just whatever that wavelength is. Okay, that's all you had to do. There are no calculations on number 12. You just have to realize that they're going to be off by the length of a wavelength.
I started calculating that one for like 20 minutes until I realized that.
Yeah.
I was pretty upset with myself.
So, because that's the only way it works to reinforce itself. Your answer to number 10 is in millimeters, something around 1, if you're in millimeters. Okay? All right, are we good? Anything else you all want me to go over? Yes?
6B, please.
Okay. So, question 6B? Yeah. All right. So, on this one, you're going to talk about what happens to the intensity of the bright fringes. So, here's the deal. So, on number 6, you've got, what are they doing? And then the width of both slits is increased. So, here's the deal. I don't remember what they changed. So, on number 6, what's going to happen is that, imagine you have this set up, okay? And this light's going to go through. And then you're going to have the same setup, and you're going to keep the same distance, but now you're going to make that opening. So basically what determines your intensity in terms of light is the number of photons that are striking the surface. Okay? The more photons that strike the surface, the brighter it's going to be. So because of the fact that you have a wider gap, now notice that this distance here, the width of the slits, isn't a factor in the equations. Okay? What's a factor is how far it is center to center. So when you open those up, all that's going to happen is that you're going to allow more light to go through. With more light, the fringes become more intense.
So look at. Okay. So.
Now, obviously, there's a limit to that. If you open this up so far, you take away, then it just becomes one opening. Okay, well, then it's not a double slit it's going on. Okay, but within the limits of still keeping it as a double slit experiment, the more you open it up, the more light's going to go through. Okay. Anything else? Going once, going twice. So, all right, buddy. Now at this point, after now you go, Jerry. Random things. All right. So first off, let's kind of we're just kind of work through this. Okay, make sure everybody's cool. So you've got this representation, right? Okay. So let's talk about this. It's a model of a type of wave. What type of wave is it? Is it a longitudinal wave or is it a transverse wave? Longitudinal, right? How do you know?
Because it's like compression.
Yeah, so this is like sound, right? So what's happened is that this could have been like a tuning fork that was vibrating back and forth, right? And so you've got a compression, right? And then you've got a refraction. Got another compression. So as that tuning fork was vibrating back and forth, right, you can conclude that, oh, this is longitudinal wave because of the fact that there's a difference within the densities. Now, in terms of this, okay, this actually has no meaning, mainly because of the fact that, because all you know is that it's a distance between like two dots. Now, you can talk about this being, this would represent like the longitude, or excuse me, the wavelength of it, because that's the distance between this contraction or this compaction and that compaction. So you could talk about this being the wavelength. This in here really doesn't have any meaning at all. But if you know the wavelength, okay, so if you know the wavelength and you know the speed of sound is, hold on, let me export this. Come on. This is what I have to go through when I grade your papers. I've got to import it into Notability. And then grade it. Well, that's why I said if I can't read it, if you guys are saying, you know, when you guys look at it, if you guys can't see it, I can't see it.
How often do you get ones that you can't read that's such...
Have you seen my handwriting? Yeah, I mean, I'm not.
No, is it like blurry or is it a handwriting thing like Gannon's saying?
Both?
Oh,
Oh,
Yeah.
that would make sense. I thought it was like blurry, like people were like shaking the phone. And
Oh, no,
taking
sometimes that
pictures.
happens too. Sometimes that happens too. Okay, so you've got, let's say for example, the speed of sound is 345 meters per second. And then that's going to equal wavelength times frequency. So if you can measure that wavelength, then you can figure out what that frequency would be. Okay? Now, so remember, those are inverse relationships of each other. Wavelength gets smaller, frequency gets higher. Okay? Home run deal. All right. Now, let's say I gave you this question. Say this is the test question. So I'm just going to shut up and try and figure that out. So, Bodie, stop that camera for a second.
Time, so can you find frequency?
Okay, so here's the deal. So what's important about this is that we're not talking about the speed of the wave. We're talking about the speed of this point, okay? So as this is moving along, right? So looking at this, let's start at the beginning. So this is going to be your amplitude, right? Okay, so it's got an amplitude of 0.6 meters, right? So it's going to, so from this point it's going to travel up 0.6, right?
Yep.
It's going to travel down 0.6. It's going to travel another 0.6. And now, because this thing is actually going back and forth like this, right? It's vibrating back and forth like this. So in a half a second, what's the total distance that thing has moved?
2.4 meters.
2.4 meters. How long did that take? Half a second, right? So what's the initial velocity of that point? 4.8 meters per second. Okay? Go with this. So that's that. Now, then, if the frequency of the wave is doubled, okay? So now it's going to be moving twice as fast, right? Okay? So instead of having the period of half a second, it's going to have a period of 0.25 seconds. Is it still going to travel the same distance? Yes. So what's going to happen to the speed?
Double.
It's going to double. So the correct answer is
D.
D.
I did all the wrong steps, but got
Yeah,
the right
I
answer,
just-
so I think I'll be fine.
Okay.
No, I was kidding.
Now, but here's what you have to be careful of. If you're talking about the speed of the wave itself, okay? So as that travels through the sound, whether it's light, whatever, what's important about this question is that you're talking about a particle that's vibrating on the string, okay? That's the whole key to this question. But if you're talking about a wave traveling through a medium, okay, that's going to be wavelength times frequency. So with that one, if you increase your frequency, the wavelength is going to become smaller. So this was one of the questions on the assignment, was that bats use, and I hate bats, but they're kind of cool, because bats use echolocation. So they send out sound waves that bounce off and then they come back. Well, that's going to be based upon a certain frequency and a certain wavelength based upon the sound of air. Dolphins are underwater. So what do you know about the speed of water, the speed of sound in water?
Faster.
It's much faster, right? So, but if they want the same wavelength, right, so they can differentiate where these schools of fish are. So if you want a higher velocity in water, but you want that same wavelength, then what do you have to do with the frequency? It has to go higher, okay? So that way you can produce the same wavelength. So dolphins will emit a much higher frequency pitch than bats will because of the fact that sound travels faster in water than it does in there. Okay.
Wait, I have a question.
Okay.
So if it were the speed of the string or whatever, Is the only way to change that then if you change like the whatever it's called, linear
Yeah,
density?
you'd have to change the medium, like you'd have to make,
But if it's a string, like not a sound wave, don't you have to change like tension?
yes, now that's the sound on the string itself as it's going through. You're not talking about the sound that you hear. That's what that equation is, that's referring to the speed of the sound, that's like, that would be the sound, that would be the speed as that travels down that length and back. But no matter what I do, what you're gonna hear, in terms of hearing that sound, that's the same. But what we can change is the sound or the velocity of the string, or the velocity of it as it's traveling down the string itself. They're two different things,
Yeah.
okay? Yeah, if I can change the tension, that's the main thing, and then your mass per unit of length. And again, if you need that equation, I'll give it to you.
But like, so if this one had said the new average speed of the string, you couldn't,
No.
there's no possible.
No.
Okay.
Now, if it said, what about the sound that you hear if you doubled the frequency?
Sure.
That sound would stay the same. Okay?
Yeah.
Got that. All right. So we'll get back to these problems because there's one I want to make sure that we get through. So, because I can hand out, I'll send out those answer keys if I have to. But let's say that you have a wavelength of 700 nanometers in air, and then in some new medium, the wavelength gets shortened to 500 nanometers. So what is the index of refraction? So let's say I gave you that question. Blah, blah, blah.
You want us to use 1.0003 as the refraction?
No.
Or assume 1?
You can just assume that, air, you can use an index of refraction of 1. Now, think this through. What does your answer have to be bigger than? 1, right? Okay, your answer has to be bigger than 1. So, what's the only way that you can get an answer bigger than 1? Are you going to take 500 and divide it by 700 or 700 and divide it by 500? 700 divided by 500, right? So what do you get?
1.4.
1.4, okay? So n is going to equal 1.4. So the bigger that is, okay, the more this wavelength becomes smaller, the more optically dense it is, and the more it's going to slow down. Now, if I said, okay, then knowing that, if I said, what is the velocity and frequency in the new medium? Okay? And yes, this is like electromagnetic radiation. Okay? This isn't sound. Because you don't talk about index of refractions for sound. And remember, the speed of light is 3.00 times 10 to the 8th meters per second.
Nano is to the negative 39. That's the first question.
Huh?
Nothing to do with that.
Okay.
I just couldn't remember if nano was to the negative ninth or
Then
not.
the negative 9.
Yeah, I figured.
Okay, so let's go through this. So what do you know about the velocity in the new medium? Is it going to be bigger or smaller than the speed of light?
Big
Smaller.
or smaller.
Smaller, right? Because the fastest it ever goes is in a vacuum. Okay? So think this through. What units do you still want to end up in? Meters per second, right? So here's the question. Am I going to multiply by that index of refraction, or am I going to divide by that index of refraction? Divide, right? Okay? So you divide this out, so what do you get as that new velocity?
2.14
2 point what?
2.14
2.14?
times 10 to the 8.
Okay? Still Hall in the mail, right? Okay? Now, to get the frequency, there's two ways that you can get the frequency. Okay? One option is that you take the speed of light and you divide it by 700 nanometers, but you got to change the nanometers into
I thought it was
meters.
500.
Okay? Or you can take this velocity and divide it by the wavelength that it has in that new medium.
Oh, it's
Okay? So you have to choose one or the other. You either take the speed of light and divide that by 700 nanometers, okay? That's 10 to the negative 9th. Or you take this velocity and you divide that by 500 nanometers. You're going to get the same answer either way, okay? It's going to be the same. And that's what's important. The frequency stays the same, okay? The frequency stays the same. So, what'd you get as that frequency?
4.28 times 10 to the 14 hertz.
4.28, whoa, that's a horrible 8. Times 10 to the 14th hertz. Okay? Cool with that. All right. Now, let's talk about sound a little bit. So, I'm going to give you, like the equations for the Doppler effect, I'm going to give you any equations that you need. You just have to know how to use them. But let's talk about this. If I talk real slow, okay, we'll call it like this, versus I talk really loud, what's the difference? What makes something loud?
The amplitude,
Why?
because there's more energy. There is more particles at the peak of the compression wave at that point
Okay?
versus if it had a smaller amplitude.
So if you're going to hear something that's loud, right? Basically, it's Daniel was right. Okay, it has to make your eardrum vibrate. So for you to hear me say the word, "Hey, we're having a test tomorrow," okay? The only way that can happen is if, number one, my vocal cords vibrate. They send out a series of compressions and refractions. They hit your eardrum. Okay. Now, if I'm talking real quiet like this, okay, y'all can barely hear me because your eardrums are vibrating. Okay. Now, if I talk loud, right, Alice going, whoa, okay, because there's more energy, and with that more energy, then that eardrum's going to vibrate more. Now, if Adeline goes to the back of the room, okay, if I'm just normally talking and Adeline starts to walk away, at some point, Adeline's not going to be able to hear me anymore. Why? What happens? Gannon, you've already answered. Adeline, what's going to happen? So, why could you hear me when you're sitting here? But if you're down in the cafe, if you go to the way back of the room, why couldn't you hear me?
In my head, it's because the sound waves have like dispersed so much that it doesn't like have as much intensity on your ear.
Beautiful. There you go. So if you look at the equation for intensity, right? Okay. which is power divided by area, which is going to be watts per square meter, right? So this area, and remember, there's two ways to look at this. One is 4 pi r squared. That's if you're talking about the energy being emitted from a source and it's spreading out in all directions, okay? If you're talking about the energy that's hitting your eardrums, that's going to be pi r squared. But here's what's important. It doesn't make any difference. As the radius doubles, what happens to that intensity? If Adeline goes twice as far away, it's going to go down by a factor of 4. Okay? If you triple it, it goes down by a factor of 9. So if you look at intensity versus radius, okay? So let's talk about the various planets as you go out from the sun. So what's this graph going to look like? So here's Venus, there's Jupiter.
Exponentially decrease.
So what's going to have more intensity? Jupiter or Venus? Venus, right? Because the sun's going to be emitting the same amount of energy, but as you get further and further and further and further away, it drops smaller and smaller and smaller. Okay? Good with that. Okay. All right. Now, let's talk about what might happen tomorrow with a boat problem. Okay?
Oh, boat.
Huh?
Boat problem.
A boat problem. So here's the shore. This is looking down from on top. Okay? This is how navigation used to be done. Okay? And you would have radio waves that would emit this sound, right? And here's Tommy the tugboat, right? And it's coming along. So if Tommy is right there in the middle, this is what I tried to show you guys with the sound, right? So if you're right there in the middle, that's what you're going to call that central maximum. That's when that sound is going to be most intense. So then you're going to get another point over here where you have another maximum and another point over here. So this is symmetrical, right? So this distance here is going to be the same as this distance here. It doesn't make any difference, okay? So what you would know is, what they're typically looking for is how far offshore you are. So if you look at that equation on how you calculate this, and it's delta y lambda L over D, okay? So here's the deal. So if you know, for example, they would know how far apart these radio sources are. Okay? They would know how far apart the antenna are. So you would know D. That's a fixed value. Okay? And they would know the wavelength. Okay? They would say, hey, we're emitting these radio waves at a certain wavelength or frequency. Okay? So you would know this number. But what you would be searching for is L. You're trying to figure out how far offshore you are. Now, think this through. The further you are offshore, what's going to happen to your delta Y value? As you're farther away, as L gets bigger, because you're not going to change the wavelength of the sound, and you're not going to change how far apart these are. So the farther out you are, the longer the greater this distance is. Now, here's the deal. So what they would have to know is if they knew they were traveling at a certain speed, okay? Usually it's measured in knots when you do like nautical stuff. And knots came from literally they would tie a string. They'd have a long string and they would have knots on the string that were a certain distance apart. And they would count, they would let that out, and they would count how many knots went by in a certain amount of time. And that's what they would count, and that's how they would measure their speed, is how many knots went by. So you could figure out, so if you knew how long it was in between these times, so you would hear this maximum, and you all did that back there, and then you'd hear a minimum, and then you'd hear another maximum. So if you knew how fast you were going, and you knew how long it was in between, you could figure out this distance. Oh, then you would know this distance. You'd know the wavelength. You know how far apart those transmitters were. You could figure out how far you are offshore. Okay? And so before they did GPS, so on the coast, every so often they would have these radio towers that were emitting a certain frequency. And you would have radio. That's what, like my dad, that's what he did when he was in the Navy. He was the radio man. And so he would listen until you hit that mixed maximum. And then it wasn't exact, but you could at least get an idea. Because if you've ever been out in the ocean, away from any land, it's kind of unnerving because you have no fixed reference points. Okay, you can't see the land, you can't see anything. Yeah, you've got the stars, okay, if it's cloudy, whatever. So that's what they would do to at least get an idea of how far off they were on the shore. So I promise you, on the test, that's going to be your first question. Okay, there's going to be a problem like that. Mark my words, that's going to be the first question. Okay. All right. Now, let's talk about this one, number 6. So, Mr. Carter, stop that camera. Okay, so I've taught here since 1993, and I've never sent out emails like this. So they just sent out an email that basically says, hey, teachers, take stuff home in case you have to teach remotely tomorrow, Monday, and Tuesday. Okay? So I'm just telling you all, tomorrow, even if it's a remote day, okay, like if they called off school, yes, you're still going to take the test. I'm just going to send it out. Okay? So the test is still going to happen. If we're actually in school, you guys, now as cold as it is tomorrow, even if you guys are at home and you don't want to get out in the cold, I completely understand, okay? Don't feel morally obligated to fight the cold and come in here if we actually have school, okay? So if you still want to take the test at home, that's cool, no pun intended. Email me and I will I'll send you the test. It's the normal routine, okay? So don't flip out. Now, problem is we're starting like an optics unit Monday and Tuesday. So, well, Monday's kind of a theory kind of day anyway.
Good news, bad.
Well, isn't this like
I don't
partially
know.
optics?
Well,
With
but optics
17
is like
is like-
lenses and
yeah.
you get into more index and refraction and things like that. So, but I am going to tell you now, because once we start into those optics, even on your remote days, it would be really cool if you could actually come into school and do those labs, because of the fact that even if you just were here long enough to get the data, even on the remote day, because literally, and this sounds, it's no pun intended, but you really need to see these optics labs,
Sorry.
because I can't show them to you in a camera. You really have to be able to see it. So, okay. So, I'm just telling you all now. I've never sent emails out like this, so I'm telling you, when you all go home tonight, not that you all use your lockers anyway, but if you do, take everything with you, because they're talking about not having school. Maybe, they're not for certain, but Friday, tomorrow, Monday and Tuesday, just if nothing else because of the wind chills, okay? So, just be prepared, that's all I'm saying. And like I said, if we're in school tomorrow, and if you're at home and you don't want to fight the cold, I completely understand. Just email me ahead of time so I can get you the test, okay? All right, now let's talk about this. So on this problem, you want to calculate the frequency of the light, right? So what are you going to do there?
C divided by the wavelength.
Yeah, so you just take C divided by wavelength. That's going to get you that frequency. Start that back up. Or did you?
I never stopped. It's going.
Okay, it's still going. Okay. I couldn't remember. So that should be 5.5 times 10 to the 14th hertz.
Yes.
Okay? Then the distance between the adjacent dark fringes on the screen, okay?
2, 6, 17.
What'd you get?
0.0672 meters.
Beautiful.
Yes.
So that's just gonna be XL divided by D, which is gonna be 0.067 meters, okay? Now, here's where it gets tricky. Now we're gonna immerse this with a fluid having an index of refraction of 1.4, calculate the new frequency. Out of here, what's the new frequency?
The same.
It's still 5.5 times 10 to the 14th hertz. There's nothing to calculate, okay? There is nothing to calculate. Now, but what's going to happen to the wavelength?
It's gonna decrease.
The wavelength is going to become smaller,
Excuse me for
therefore,
a quick end of the day announcement. Students and staff, please make sure that you take materials with you before you leave school today, just in case there is bad weather tomorrow and Monday.
and on D, it
Just want to make
decreases.
sure everyone is prepared in case we go full remote. Also, if you are in a WSU Tech class, please know that WSU Tech is going full remote on the next 3 days. So just to prepare you for that. Thank you. Be safe out there.